Assalamu alaikum everybody. So what we're gonna do is we're gonna start complex numbers. So for for a lot of years, people have asked the question uh, uh, when they started having polynomials. They wanted polynomials. They had this specific polynomial, and if you look at the roots for this equation, basically, when means the solutions to the equations the this equation, people couldn't find that out because if you look at the quadratic curve, it does not intersect the x-axis, and in order to find these complex solutions you have to intersect the thing is here we're taking the x-axis, this to be the number line, and the number line is where our sort of roots lie, and if your function intersects, that's where you can have a root. But instead of taking the number line, we extended ourselves to a plane. Instead of defining the number to number line, you can go from 8, 7, 6, minus 8, minus 7, minus 6, minus 5, minus 4, 1, 2, 2, 1, 0, and 1, 2, 3, 4, 5. You can go parallel here, but you can also go perpendicular to this with another component here. And so you have I, 2i, 3i, and we define I. Now, what's I exactly? I'm coming on that. X squared plus 1 is 0. So x squared is equal to minus 1. X is equal to root of negative 1. When root of negative 1 is what we call I. Now, this is sort of like vectors because vectors have components, and there is a real and imaginary part. I need to tell you, real and imaginary parts are like I and j components of a vector. Why? Because I dot j is because when you must have studied vectors, you must have known that I dot j, the unit vectors, they're always zero. I dot I themselves are always one. Now, why does that really happen? So it happens because we're taking the dot product of two parallel components, two perpendicular things, and two perpendicular things. Dot product basically defines the relationship of cosine theta, and cosine 90 is zero. So yeah. So it's sort of something like that, where your real part and your imaginary part are, yeah, like I had and J had. But it's a little more than that. That's why the real parts are always taken as the same thing. Like we compare the real parts, like um, we basically define a complex number as this. But there is a real part to it, and there is an imaginary part to it. Now we define this real part as a real number, the real component, and every real number is also a complex number with y as 0, right? And just the numbers which are completely imaginary, they have x as 0. But the numbers which have x and y both are non-zero, uh, non-zero, then we have a complex number, and that means that it does not lie on the axis; it lies somewhere in the plane. So instead of taking a one-dimensional inputs and one-dimensional outputs like the normal functions, we're taking a two-dimensional input here. And the thing about complex is the complex roots arrive from polynomial equations, and there is something called Descartes rules of signs, a rule of signs, which means that change of signs of a polynomial will indicate their positive real roots. The ones which do not have positive real roots, if you get the negative real roots, or you can get complex roots. Now, there's one thing to emphasize here. There's always x could be I plus and minus. Thing is, there will always be two roots. If there will be a complex root, there will always be another complex roots. A complex root. So there is, for example, if I want to represent this, this is my root. Let's say this is figure x plus y, and I want to represent this. So what do I do? Is this is my z is represented by complex number. So z star is sort of the complex conjugate where the imaginary part sign is flipped. And to look at it geometrically, imaginary part is this y-axis, so it's on the other side. It could be this one is my real root and this one is was my the root I was talking about, but the sign flipped, so this was the conjugate. But whatever happens, the sign flips and it sort of like makes sort of a, you can say, reflection in the real axis. Uh, so yeah, that's what happens. And this angle right here is called the argument of the angle. And the argument is calculated by finding the tangent. Let's just erase this. The argument is calculated by finding the tangent inverse. If you look at this, tan inverse of x over y, like x and y. So tangent inverse of y over x. But obviously, the argument will change here because this is theta here. Basically, the anti-clockwise angle from the x-axis, the positive x-axis. So here we'll take the tan inverse and we'll sort of have pi minus that. Then we basically have this. We have this plus pi plus this angle tangent inverse y over x. And then we have the other side. So you sort of have tangent inverse y over x and negative tangent inverse y over x because sort of the negative angle. And if I put negative here, uh, tan and tan inverse as well, then it's gonna be that's just like common sense. If tan minus x is minus tan x, it's in sort of an odd function, you can say. Basically, if I take it to the negative side, basically, if I take negative input of the same input, like I'm taking an input and then I'm taking the negative of that input, then I'm gonna get the same output as that I got with the positive output, except for that output is gonna be negative. It sort of has rotational symmetry of uh 2 degree 2, sort of, we can say that about itself. Sine is also an odd function. Cos is an even function due to its symmetry about due to its translational symmetry about the y-axis. But that was not the point here. So this was the argument. But what's really uh, why do we need to calculate the argument? Can't we write it in this form? Actually, this form is good and it's nice, but there is another form that we usually write it. It's called polar form. Polar form again includes two coordinates because we have a two-dimensional number plane. Now you cannot extend the complex numbers to be mindful that to three dimensions because doing that would simply not make sense. The math wouldn't work. So you have two coordinates, I said, for this polar system, new polar system that I'm talking about. One is the argument, which was tan inverse imaginary part over real part. And it could be different for different cases, but for we're taking for positive x and y. For x and y greater than 0. But what is the real part? Sorry, what is the other coordinate? Now, the other coordinate is something called r, or you can say the magnitude. Now, the magnitude of a complex number is always calculated if, for example, I have 1 plus 2i. Let's just generalize for x plus yi. Then I need to calculate the magnitude for this. Okay, how do I do that? Now, this is, as you can see, this is the complex number. And this is what we call the magnitude. Now, how did I get this? That's, well, that's not exactly a good question, but like you have to look at it geometrically again. This is theta. Theta is not really important. Like it's important, but not for finding why this is. This is the x part and this is the y part. In order to find this hypotenuse, don't I use the Pythagoras theorem and x squared plus y squared? Now here we noted that you might say something like uh, Why didn't we really just yes, so that's why it's x squared plus y squared. You might say, why are we taking I or something? Thing is, we're just talking about the structure here. We're not talking about if this represents I or something. We're just talking about the length of this piece here. And if you look at it, can I represent x? X can be represented by r cosine theta. Well, r cos theta, yes. Y is r sine theta. Damn. Which means we can represent the complex number as r cos theta plus I r sine theta. I hope you can see it. Yeah, r cos theta plus I r sine theta. We can take the r common here and we can just say cos theta plus I sine theta. Now the next part that I'm gonna tell you, it's kind of a little bit mathy, so just better watch it. Now mathematicians found out later on, not later on, okay, whatever. Not going to history of that. But thing is, you can write every function as a polynomial. Every function can be written as a Maclaurin series. Oh, the board says. Yeah, every function can be represented as an infinite polynomial, which basically means including functions like sine x, exponent of x, and cos x. And those will be all the functions we need. But how do you represent them and how do you even find them? So the general formula is basically this somehow does work. Just assume it works for now because that will take a while to say why it works. FNA. I'll just first kind of like write it, then I'm gonna. Okay, this is the general formula. And since you can see, you can look at this, A is just a constant, it can be any number. Any number, and Maclaurin series is this favored Taylor series, this favored special case of Taylor series where A is equal to 0. So we take this series as sum to infinity fn 0 x n over n factorial. Now, how does this work? That's not really important, but if you graphically look at it, if you look at a picture of it, it's somehow like sine x is somehow like this, right? So let's say this is 0. And obviously, we're talking about Maclaurin series being like working at 0. So it's obviously gonna first start working at 0. And then it's gonna work out its way from there. So if I write for sine of x, so first I differentiate this sign by here, by the way, this sign means number of times you differentiate a function. So yeah, if I differentiate sine x, that's cos x, right? So can I say first we begin with 0, which means it's sine x itself. Sine x, cos x, minus sine x, minus cos x, blah blah blah. So where's the sine x? And x to the 0 divided by, and sine of 0, which is 0. So we just ignore that term. Cos. And every sine term ensuing, because ensuing sine term, so cos x and minus cos x and minus cos x. And obviously the powers is going to be like 1 and 3 and 5 and 7 because we're skipping the even powers here. Because it's like cyclic, you know. I take it back to sine, back to cos x minus. The function itself repeats and sine of 0 doesn't make sense. So I sort of go back. So I'm going to have odd powers of x, and don't forget the n factorial. X minus x cube over 3 factorial will be like cos x. Cos 0, that's 1. So we just ignore that here. However, minus cos x is coming. So every alternating term is supposed to be negative. That's why I put this negative here. So sort of be something like this. Now, this does work. You can look at it because, first of all, yeah, so this does work because something sine is something like this, and if you we're approximating it at zero, so it's gonna start from zero, and since it's gonna go from zero in both directions, so it's gonna go in positive and negative directions equally because it's like it's that series is it like starts at zero. It's like series originates it's locally. What can I say? It's basically it's local. You can say because Taylor series allows us to keep any number here, but zero works best for most cases, except for a few cases like ln1 plus x, where we ln x, sorry, where we cannot take the Maclaurin series, we have to take ln1 plus x. ln x itself, you know what we're gonna have. So if I take this, then I have something like if this is zero, sine x, sine x minus x cubed would be something like if you look at it, be something like this, x minus x cubed plus x5, and then the polynomial's degrees keep increasing, and it's gonna approximate all the way to infinity, and those are all the terms which originate go away from zero to infinity, and that's why we don't consider those terms. They're not like we don't like those terms become smaller. That's not the point. It's like they go away too much from your from the point from zero we're talking about, and we're talking locally at zero. So why do we have to care about those other terms that go away to positive infinity, negative infinity, or like go just go away basically? It approximates locally pretty fine. So yeah. So this was the thing, and sort of have this formula here, and it does work geometrically. I don't really have proof for this, but there's one thing that I'm going to show that the relation between e to the x, cos x, and sin x. And what do I have to prove here? I have to prove this part. E to the ix is equal to cos x plus I sin x. This should be what I have to prove. But first, I need to define all the functions. Okay. So let's make it easier for me. Sin x, I already told you, is going to be something like x minus x cube over 3. I'm showing it in that, you know, the summation form is much harder to remember. So I'll just show like first four terms, uh, e to the, uh, now for cos x again. Now we got to differentiate it, that's minus sin x. Differentiated again, that's minus cos x, and differentiated again, that's sin x. Sorry, that's sin x. So cos of 0 is gonna be 0, sorry, 1. And you had x to the power, now x to the power 0 here, x to the power 1 here, x to the power 0 here, divided by 1 factorial itself. So 1, okay. Sine 0, so the sine terms just cancel out, and you cos and minus cos, cos and obviously it goes back to cos. So cos and minus cos, cos and minus cos. So again, there is gonna be these alternating sort of, you can say, um, sine terms, but now look that the power is gonna be even here, or 2 factorial. So this is gonna be x 1 x to the 2 divided by 2 factorial plus because all minus cos x minus because of the negative sign here, and cos 0 is 1, so we're just not gonna we just keep gonna ignore that, and somehow we're gonna end up with this, right? And you can say it keeps on going. What is e to the x? E to the x is something like, first, what's the function of e to the x? The derivatives just keep on going, e to the x, e to the x, e to the x. This is the simplest. E to the 0 would be 1. Okay. E to the 1 is, sorry, we're not talking about e to the 1. 1, sorry, e to the 0 again 1. So there's going to be a 1 coefficient. We're just going to keep ignoring that. There's no negative sign here. There's no reason for a negative sign to be there. So we're just going to get x again divided by 1 factorial, x squared by 2 factorial, x cubed by 3 factorial. And it's just going to keep on going. That was quite simple compared to these. Even these were also simple. Now I want e to the ix. Now here, I is a number that if I squared it, I got minus 1. What happens if I square minus 1? Obviously 1. What happens if I square 1? Sorry. I got it wrong. I got the wrong thing. If I multiply I with itself, that's minus 1. If I multiply I with minus 1, obviously minus I, anything multiplied by 1, then there's going to be negative sign. What happened if I multiplied minus I with 1, minus with I? Very good. I square, which is minus 1, minus minus 1 plus 1. I multiply with I again, I get this sort of, you can say, cycle that will help us here. There is going to be ix plus, then we're going to have negative 1, so negative x squared over 2 factorial, negative ix cube over 3 factorial, all of these terms. You might say, okay, let me expand it for you here. E to the ix, right? Let me make it more clear. E to the ix is going to be 1 minus ix, sorry, plus ix, plus, sorry, minus x square over 2 factorial, plus, oh, minus again ix cube over 3 factorial. And then I'm going to get x4 over 4 factorial. So x4 is that's just 1. So x4 over 4 factorial and sort of keeps on going. If I look at sine x, if I look at this here, cos x is 1. This is a cos x term, right? This is a cos x term, right? This is a cos x term. We're getting cos x terms here. And if you eventually keep on repeating it, you'll get cos x terms. And the rest of the terms, what are they? Well, they're not sine x terms. But if you put an I behind them, they become these terms, which are exactly I sine x terms. So you have cos x plus I sine x, which is e to the ix. Now this is a wonderful relation, and uh, before I just tell you what is considered the most beautiful formula in maths, I want to say that this took a while. So yeah, you need to appreciate it. And this sort of also shows on uh like your geometrically, and physicists use e to the I theta as, yeah. Now we're talking about x. We're taking x as a real part, so we're taking theta as an argument. So right now we're saying e to the I theta is cos theta plus I sin theta instead of x here, which is obviously same thing. If you can see it, you would definitely see it. That's what I mean. E to the I theta is used as phase, like direction and rotation. Let me allow me to uh, visualize. Z is a complex number. It's 2. What does Z2 mean? Which means, it sort of means there's a circle of radius 2. You'd be like, okay, so do you mean R is 2? Well, R is 2, but R is 2 could be any point. Z is 2 is all the points, the difference here. And Z can be represented by, since we said e to the I theta cos theta plus I sin theta, this was actually x plus iy. So do you see that Z can be represented by R e to the I theta? R, if Z is 2, then R is, let's say it's 2 here. and e to the I theta. E to the I theta is basically just a unit circle. Basically, if I just take this to be 1, then it just creates a unit circle of radius 1, and it sort of shows you your theta could be any point on the circle. Get me? So if theta is like 5 or 3, it could be something like this. And I can locate it on the circle. That's sort of how phasors and spinors work. And sort of your AC circuits and quantum quantum field theory, respectively. So something like that. That's how we can create a circle and locate points on a circle, and we restrict that circle with having a given radius. So that's what it is. So we consider z is equal to e to the I theta. Now, obviously, let's just do the a little bit of the easy part, like just a little algebra as to what complex numbers are doing. So when you sort of multiply two complex numbers, if you take a square of complex number, let's just say, then it's gonna be x squared. Sorry, yeah, whatever. Actually, let's just take the square for now. X squared plus yxi plus yxi plus um, y square I square. This will eventually lead down to x square minus y square plus 2yxi, sort of the same thing as a binomial formula, and you can take we usually use square when we have to find the square root of something. We can say that some number squared is, let's say, this number. So I have to find this, I can compare. Now, always the thing about here is that you get two separate parts, and there's two separate parts here as well. So what we have to do is always compare the real parts and compare the imaginary parts. That's something we have to equate because they are two different components. As I said earlier, they're like two different things. Like when we divide things into components and we sort of equate forces, they're sort of the same thing we're doing because those two components are perpendicular to each other, so they have nothing to do with each other, the cos and sine components. That's why it makes it easier for us to sort of get that. Yeah, that's why we compare the now complex numbers. Especially in quantum mechanics, when we wanted to find the probability of something, you have this condition that probability should be integrating the probability density, infinity to zero probability density function, which was actually the modulus squared of the wave function, to be one. But there needed to be another condition. Okay, probabilities add up to one, but what if the probability was, let's say, less than 1 or less than 0? It could be the modulus of the probability, which we represent by this sort of thing. It could be between sort of you could say negative 1 and 1, sorry, 0 and 1. So why, how do we actually confirm this? This was just an example, but how do we know that it does not lie in negative 1? Thing is, when we talk about something like this basically refers to, yes, it refers to the magnitude of the complex number. And you might say, what? Did I tell you that the magnitude looks something like this? Yes. And why did I tell you that the magnitude looks something like this? Because the Pythagoras theorem, the triangle. But if you think about it, can we get it like that? I told you that this is Z and this is Z star, which was a complex coordinate where the imaginary part has switched its sign. So if I multiply the complex number with the complex conjugate, what do I get? X squared plus xyi. Let's see what happens. Minus xyi minus y square I square, which really just gives us minus 1. So it's like, and these terms get cut off. So yes, we got x squared plus y squared. That's interesting. Yes, it is interesting. Hmm. Now, listen to me. The magnitude squared was because the magnitude was not x squared plus y squared. I think I made a mistake earlier. It's actually root x squared plus y squared. So uh just look at that mistake. So that's why we have the magnitude squared here. And that basically just magnitude squared just ensures that the probability can never be negative because these two things are real. If x and y are real, and you get the square of two real numbers is always positive, and the sum of two positive numbers is also again always positive. So that was somehow how magnitude can never be positive. Also, if you look at it, if you've seen polar coordinates, r is sort of like displacement from the origin. Displacement like the distance, shortest distance here. So why do we how can you represent negative displacement? It's not possible, right? Even if you lie somewhere here on the plane, this is still distance, displacement. We're not talking about x and y components respectively. We're just talking about the displacement. It can never be negative. So that's how it can never. And you take the root of a positive number, it's gonna always be positive. And you square it or you root it, that does not really matter because at the end, suppose we know that x squared plus y squared itself is a positive number, so that doesn't really matter. Okay, so there's some other stuff like things about axioms and stuff, but I'm gonna do the interesting part of complex numbers. Now, a complex number is something like this, right? Yeah. What if I squared it? R square e to the I 2 theta. Hmm, nice. Because of obviously thing gets squared and the power rule for square for power rule basically just multiplies with taking the power. Okay. And so we can sort of say, can we say r cos theta plus I sine theta whole square is like r cos 2 theta plus I sine 2 theta? You might be like, wait a second, what? R square first. Because here I theta is the same as cos theta plus I sine theta, and I 2 theta is 2 theta just the input instead of theta. So can we say cos theta plus I sine theta will be cos 2 theta plus I sine 2 theta? Well, I mean, it makes sense, but to build intuition behind it, let's just prove it for some cases at least. So let's prove it for um uh yeah, it's actually this. So we need to prove it. What do we do? Let's just take it for 2, for example, here. So if I take r squared cos square theta plus, I don't know, 2I cos theta sine theta, obviously I squared minus sine squared theta. Hmm. Well, that's interesting because cos squared theta minus sine squared theta is actually cos 2 theta from a trigonometric identities. That's cos 2 theta. And 2 cos theta sine theta is actually sine 2 theta from my trigonometric identity. So that's like plus I sine 2 theta. That does make sense. But since we don't rely on something that, oh, it makes sense, it's rigorous enough, we have to prove something. Now, you cannot just say, you can say that if something has an exception, it does not work. You can prove by contradiction. But we can clearly not say if something works for everything we've tried on, it works for everything there is. We don't know, we might find an exception. But to find a generalized proof, that would completely destroy all sorts of exceptions that could possibly appear. And that's why many mathematicians are stuck on finding proofs to things which they know are true, sort of feel are true, 100, like 99.9% are true, and have literally found no exceptions to it, but still their proof, like either the proof is not rigorous enough or they don't have a proof. That's basically it. Do this. So I'm gonna prove this by induction. So that would be enough for all n. I don't have to prove for q, for and for ongoing all for infinity because that would just generalize my proof. There are three steps for proof by induction, and it means we're proving it true for all positive integers, you can say, because we usually say prove true for n is equal to 1. Now let's prove true for n is equal to 1. Cos theta plus I sine theta. We're gonna say this is true for cos theta plus I cos theta plus I sine theta, like n. Sorry, cos n theta plus I sine n theta. If I take 1, would 1 make sense? 1, same thing. That would be cos 1 theta plus I sine 1 theta. So I don't really get the difference here. It's just the same. It's just the same. So that's what we're done. Proof for n is equal to 1. Now we need to assume true for n is equal to k. We need to assume that for some integer k, this equation holds. Okay. This is something we're assuming. We're not going to prove it because we're saying this is true. We're taking it as true. We're taking this for granted, sort of. And we need to prove, what we actually need to prove is cos theta. I'll just erase this part because this was just one step for us. And we already have to take this and is equal to. So what I have to prove is I sine theta k plus 1 is basically cos k plus 1 theta plus I sine k plus 1 theta. How do we prove that? Think about it. First, what we can do is cos theta plus I sine theta k and divide this in cos theta plus I sine theta. Does that make sense? Yeah, that makes sense. And since we already have this, we can say cos k theta plus I sine k theta, and then we multiply it with cos theta plus I sine theta. Now's the whole thing. To multiply, we get cos k theta plus I sine theta cos k theta plus I sine k theta cos theta plus I minus sine k theta sine theta. Now it will be interesting to note that they're actually two different parts. Now we have to look at it in real parts and imaginary parts. The real part is this and this, imaginary parts is this and this. If you look at the real part, look closely. This is cos k theta minus sine k theta sine theta, cos theta minus sine k theta sine theta. Isn't that the same as cos sort of a plus b compounding the formula? That's cos k plus 1 theta because k plus 1 theta. That makes sense. That makes perfect sense. And if we just sort of isolate i's away and we just look at this imaginary part here, uh, sine theta cos k theta plus sine k theta cos theta. So, well, yes, it's sine k plus 1 theta. Hence, we proved it by induction by parts. And if we proved it for k plus 1, then so is it true for k plus 1, which is k plus 2, and so on for all positive integers. Yeah, that was it. I think I'll make another video on complex numbers, but I think this was enough for now. So, yes. Thank you, guys.